Hi friends, see in part 1 of fluid mechanics or mechanical properties of fluids we discussed about Bernoulli's principle and Bernoulli's theorem, and also I have derived the equation in terms of two formulas. One is P by rho g plus V square by 2g plus H is equal to constant. This is in terms of head. Total sum of pressure head, velocity head, gravitational head or potential is equal to constant. Okay, and also one more equation P, that is P plus rho V square by 2 plus rho g H is equal to constant. That is total sum of pressure energy, okay, kinetic energy and gravitational energy. Total sum of pressure energy per unit volume, kinetic energy per unit volume, okay, gravitational energy or potential energy per unit volume is equal to constant. You can express these two formulas for Bernoulli's principle. So that was the thing we have discussed in part 1 of fluid mechanics, that is mechanical properties of fluids. Now today we will do the applications. Very important applications of Bernoulli's theorem. Application of Bernoulli's theorem. See, in general thing, if you discuss regarding applications, you have so many examples for Bernoulli's theorem in general way. Okay, that is, for example, in a room, suppose small piece of papers are spread on the ground. If the fan is switched on, then the papers will be moving here and there. This is also due to the Bernoulli's theorem. That means whenever there is a high velocity, pressure becomes less. ఎప్పుడెప్పుడైతే మనకి వెలాసిటీ ఎక్కువ ఉంటుందో ప్రెజర్ తగ్గిపోతుంది, then the body is lifted up. That is general principle. And not only this, we have some more examples also in nature. Due to the Bernoulli's theorem or Bernoulli's principle, you can see when hurricanes occur, Telugulo tufan antaru, tufan. Okay, so when hurricanes occur, what happens? You can see at some places the boards are going away. That means in buildings the upper part is flown away and the down part is left. You can observe that one in nature. So whenever you are occurring hurricanes, okay, whenever you are having a tufans, low pressure tides, huge velocity will be coming. So due to that huge velocity, the top portion of the building or hut is flown away. This is because of, again, Bernoulli's theorem. Okay, so like this, so many examples are there for Bernoulli's theorem applications. Okay, now let us see the main application of Bernoulli's theorem in the intermediate examinations, that is Venturi meter. Venturi meter. So in Venturi meter, how you will apply Bernoulli's theorem we will see today. Very important. Okay. So in Venturi meter, first of all let us see what is Venturi meter. These things will be studying in engineering when you go to higher classes in fluid mechanics lab. So this Venturi meter and ఏమీ లేదండి, see, like this structure will be there, pipe, okay, with unequal cross section. Okay, so let this area be A1, let the pressure be V1, P1, and the velocity here be V1, unequal cross section. Now this is connected. Another small pipe again, followed by again like this. So this is the basic structure of a Venturi meter. Now if you see here the area of cross section is more. You can see here the area of cross section is less here. Okay, for example, if you connect a tube here, okay, and one more tube here, you can observe here the area of cross section is A2. Here if you observe, A1 is greater than A2. This area is less than this area. Okay, so when the fluid is coming inside this pipe, when the fluid is flowing here, you can see what is the equation of continuity? A1 V1 is equal to A2 V2. That means what happens here? Area is inversely proportional to velocity. More velocity, less area, more area, less velocity. That means here the velocity, if it is V2, it is more than V1. Because V1 is the velocity at this end. Let this end be P. Okay? Let this be Q. So ఇక్కడ మీరు గమనించినట్లయితే you can observe here this area is more than this area. Less area, more velocity. When velocity is more, pressure becomes less. So here, whatever fluid is flowing, you can see this is the water level and here this is the water level. Here pressure is more, here pressure is less. Let this height be H1 and let this height be H2. And the difference in these heights, let it be H. That is H1 minus H2, that is the difference in the heights. Okay, height difference. So why the pressure is down here? More velocity. According to Bernoulli's theorem, whenever the velocity is more, pressure becomes less. Okay, less area, more velocity. So for example, you can see that this is the horizontal axis of this pipe. This is the horizontal axis, x-axis. Now suppose if you apply at these 2 points, point 1 and point 2, if you apply the Bernoulli's theorem, we'll see what happens. Bernoulli's theorem, you are having two ways. One is in terms of pressure head, another is in terms of pressure energy. So let us take the second formula, that is at here at point 1 I am applying. General formula first I am writing P plus rho V square by 2 plus rho GH is equal to constant. This is the Bernoulli's theorem formula. That is total sum of pressure, energy, kinetic energy, gravitational energy equal to constant. Now you can observe the horizontal axis is same height. There is no height difference. That means what happens? H1 is equal to H2 here. So if you apply here, what happens? What is the pressure here? For example, P1 plus density. Density means density of the fluid is constant. So rho. So what is the velocity here? V1 square by 2 plus rho GH. Because both are at same levels, this point and this point. So height difference will be 0 of course, but we are writing here as H is equal to, what is at 2 pressure? P2 rho V2 square by 2 plus again rho GH. So because here the height is same, this item will be cancelled. This item will become cancelled because both are at same heights. Now observe carefully, here the velocity is more. Velocity ఎక్కువైతే ఏమైంది? Pressure తగ్గిపోయింది. More velocity, less pressure. That means here P2 is less than P1. That means P1 is greater. So P1 greater కాబట్టి you will subtract from this one. So P1 minus P2, okay, P1 minus P2 is equal to which velocity is greater? V2 is greater. Therefore rho V2 square by 2 minus rho V1 square by 2. Clear? So here what? P1 minus P2 means pressure difference between the 2 points at this end and this end, because here the pressure is less, more velocity. More velocity means more kinetic energy per unit volume. So therefore here P1 minus P2 is equal to, I can take common rho by 2 into V1 square minus, V2 square minus V1 square. So this is the equation of Bernoulli's theorem when you apply for Venturi meters. When you apply for Venturi meter. And you already know what is pressure formula. Already know you have the pressure formula. What is pressure formula? Rho GH. Pressure is equal to rho GH. Okay? Because rho is the density, G is axial length gravity, and H is the height level difference. Okay? And here you can see the height of the liquid. Here H1 is more than H2. So what is the difference in heights? H1 minus H2 is equal to H. This is the height difference. H1 minus H2 is equal to height. So this is how you can apply the Bernoulli's principle or Bernoulli's theorem for Venturi meters. and thereby you can solve any problem. You can solve any problem by using this principle. That is total sum of pressure energy, kinetic energy and gravitational is equal to constant. Clear? Please note down. Very important application. Now, after studying about Venturi meter, let us go still further. After studying about Venturi meter, let us go still further. So, this is one of the major application in Bernoulli's theorem. Now, after this, we will go. We have some numericals also. You can solve the problems by using these problems. Okay. Now, next one in our IPE, that is Torricelli's equation. What is that one? Another scientist named Torricelli. Torricelli's equation or theorem. Another scientist named Torricelli's equation or Torricelli's theorem. Now, what is this Torricelli's equation? Let us see. For example, you have a tank like this. For example, this is an open tank, please, not closed. Open tank. Now, for example, you have a small hole here. Small hole. And for example, from this hole, for example, the fluid is coming out, water. Okay. Now, let the total height of the tank be capital H. Total height of the tank be capital H, and let this be the reference axis, reference line, and let this height be, say, small h. Let the height be the whole height from the reference line, hole where the hole is drilled. Okay, small h. Now, suppose liquid is there here. Now, the question is, Torricelli's equation theorem question is, with what velocity the fluid is coming out from the hole? We have to find out the velocity. Okay? We have to find out what is the velocity with which the fluid is coming out. So, we have to find the velocity of the fluid coming out. That is Torricelli's theorem. Now, here you can go with the Bernoulli's application. We will apply Bernoulli's theorem. So, applying Bernoulli's theorem at 2 points, point number 1, point number 2, and as you see, the open tank is exposed to air. You are having atmospheric pressure P0, and this is also open, atmospheric pressure P0. So, when you apply Bernoulli's theorem at 1 and 2 points to get Torricelli's equation, let us apply. What is the formula? Actual formula? P plus rho v square by 2 plus rho g h is equal to constant. This is Bernoulli's theorem. Pressure energy, kinetic energy, gravitational energy. Okay. So, what is the pressure at the first point? Atmosphere pressure P0. Okay. So, what is this one? Pressure. Atmosphere pressure is there, P0. Okay. Now, if you observe carefully the tank, it is filled with water. It is completely filled with water. So, when it is filled with water, it is exposed to atmosphere pressure. Atmosphere pressure units and ATMs, 1 atmosphere pressure. And you know what is 1 ATM? 1 atmosphere pressure almost is equal to 1.1 into 10 power 5 Newton per meter square or pascals. SI unit. Okay, ATM value anta తీసుకోవచ్చు 1 atmosphere pressure generally nearly 1.1. 1.1 into 10 power 5 Newton per meter square or pascals. So, at this point, what is the formula of Bernoulli's theorem here? Atmosphere pressure P0 plus density, and what is the velocity here? Here any velocity is there here? Huh? Because water is coming from here. So, here you don't have any velocity. Okay. So, here velocity you can put 0. In the place of V, let the velocity here be V1. Let the velocity be here V2. So, here velocity is 0. 0 whole square by 2 g h. What is the height here from this point? H. So rho g h is equal to, same thing again apply at the point 2. So at point 2 kuda emutundi, again atmospheric pressure is there. Open kada, P0 plus rho. What is the velocity? We don't have to find out. That is V2 whole square by 2 plus rho g. What is the height? Because you have taken that as a reference line, height is 0. So into 0. Now P0 will be get cancelled. Okay. And you can see here this is also 0. Now here you are left over with rho g h is equal to rho, this is also again 0, height level, is equal to rho v2 square by 2. Rho cancel. So 2gh under root is equal to v2. Chusara? This root 2g, this is also you can find out the kinematic equation. You can use kinematic equation. V square minus u square is equal to 2as. Water falling down, that is v square, initial velocity is 0, whole square 2as, 2gh. H. So you can use the kinematic equation also to find the velocity of the fluid coming out from the hole, and also by using Bernoulli's theorem. And this is called as Torsell's equation or theorem. Same equation you can also find out by using kinematic equation or by applying Bernoulli's theorem. So root 2agh అంటే ఇక్కడ velocity బయటికి fluid ఎంత velocity వస్తుంది? V2 is equal to root 2gh meters per second. Clear? So this is very important derivation for IPE and also for numerical problems. Please note down. Right. Now let us go to the next thing. Clear? So root 2gh is the Torsell's equation, very important. You can go in different methods. Okay. Now same tank, we'll go for next thing, that is for the same tank. For example, this top area, say this is capital A. Okay. Suppose the top area is capital A. In the same way, for example, you have a small hole at the bottom. For example, ఈ బాటంలో చిన్న హోల్ ఉంది. This is hole. Suppose this whole area is say small a. This is a tank filled with water. Top area is capital A. Bottom a hole is there. That area is small a. Okay. In such cases, okay. Suppose same thing again. Here the water is coming out, or suppose it is closed. Water is coming from here. Okay. I'll close that one better. I'll close this one. Okay, na? I'll close that one. This is water. Okay, clear now? Now top area is capital A, bottom whole area is small a. Water filled in the tank, capital H is the height of the tank. Now the question is, what is the time taken to completely empty the water from the tank? Enti? Completely empty. Completely empty. How much time it will take to empty the tank? So the formula goes like this. Capital A by small a root over 2h by g. Okay. This formula already you are familiar. Freely falling body, time taken to reach the ground. Apart from this, area is added here. Capital A by small a. Capital A is the top area of the tank. Small a is the whole area at the bottom. And 2h, height of the tank. G, acceleration due to gravity, 9.8 or 10 meter per second square. So this is the formula. Small t is equal to capital A by small a under root 2h by g. This is the time taken to completely empty the tank, not half or 3/4. మొత్తం వాటర్ అంతా ఎంటీ చేయడానికి ఎంత టైం పడుతుంది? That is capital A by small a root over 2h by g. Clear? Very important formula, this one. Let us go to the next one. Now next one is, for example, see here, this is the tank, and for example this is hole is there, water is coming out, fluid from the hole, and let this height be small h. Total height of the tank, this is the height where the hole is drilled from the top, and water is falling here. Now the question is time taken by the fluid to fall here. What is the time taken? Okay. Now what will be this height? Can you tell me? This height is nothing but capital H minus small h mathematically. This height ఎంత అవుతుంది? Just like in kinematics, height of the tower. Total height minus this height, h minus capital H minus small h. So ikkadi nunchi time ఎంత already you derived there, root over 2h by g in kinematics. But here what will be? Root over 2 into, what is the height here? 2 into capital H minus h by g. Therefore, time taken is given by root over 2 into capital H minus small h by g seconds. That means from this hole, what is the time taken to fall on the ground? 2h by g. That means 2 into h minus capital H, height of the tank, small h, the hole where it is drilled, the height of the hole from the top. Okay. So this is the time, g 9.8 or 10 meter per second square. Sometimes you'll be asking what is the range also, range of the fluid. So what is range in kinematics? Horizontal velocity into time. So here range is equal to horizontal velocity anta. What is the velocity got just now? V is equal to root 2gh. That is root 2gh into time. What is the time? That is root over 2 into capital H minus small h by g. This is the horizontal range. This is the range. That means at what distance from the vessel or bowl the water is fluid is falling. Now take it inside this formula. Take it inside. Mathematically we will solve now. If you take inside, what happens? See, R range is equal to root A into root B, root AB. So under root, okay, I will put it inside 2GH root A into root B. Under root I will take and multiply this one. 2 into capital H minus into G. G cancel. 2 2s are 4. From root take away outside. So 2 will come outside. So inside root em migultayi? 2 2s are 4 నుంచి 2 outside వచ్చింది. లోపల ఏం మిగిలింది? H into H minus small h. Now here the question is, what is maximum range? What is R max? అంటే maximum range fluid ఎంత దూరంలో పడాలంటే ఏం చేయాలి? Hole ఎక్కడ drill చేయాలి? Where the hole should be drilled? At what height from the beneath? So here, if you want maximum range, see here for maximum range, if you put H is equal to H by 2, if small h is exactly drilled at the midpoint of the vessel, then what happens? We'll check it. R is equal to 2 into root over H is equal to enta now? H by 2 bracket H minus H by 2. So H minus H by 2 enta LCM kadte again H by 2. That H by 2 and H by 2 enta avutundi? 2 బయట లోపల H by 2 and H by 2, H square by 4. So this is nothing but what? 2 into H square root enta? H. 4 square root 2. 2 gets cancelled enta? H. So what is the maximum range? So maximum range fluid padalante at what height the hole should be drilled? At height equal to, చూడండి ఎంత వచ్చింది? R. So R is equal to H. అంటే height of the ఎంత ట్యాంక్ ఉందో అంత రేంజ్ వాటర్ పడాలి. ఎప్పుడు పడుతుంది? When the fluid will fall at that much distance, when the hole is drilled at a distance vertically equal to how much? ఇదిగోండి H by 2. Exactly at the midpoint, if you drill the hole, maximum range the fluid will be going. So these are very, very important in torsionless equations. Okay, please make a note of all this. Now we are going to the next derivation, IPE. Very, very important in Torsell's equation. Now I am going to the next part. Okay. Now intermediate examination IPE, they are asking one more question regularly. This may be 6 plus 2. It may be 4 marks or maybe 8 marks also sometimes. That is, by using Stokes' law, how to derive the terminal velocity of a raindrop. Okay. By using Stokes' law ఉపయోగించి how you will derive the terminal velocity of a raindrop. That is the next derivation. It may be taken as 4 marks or 8 marks. Very, very important, please. Okay. So next ఏంటంటే Stokes' law. By using Stokes' law, how to find the terminal velocity of a raindrop. మనందరికీ తెలుసు చూడండి. What is Stokes' law actually? Stokes scientist. Viscous forces, that is opposing force, given by 6 pi eta r v terminal. This is the Stokes' law form. That means opposing force acting in the fluid air. Okay, during the motion of any object in the fluid. So this is given by scientist Stokes. Viscous forces. 6 pi constant, eta coefficient of viscosity, r is radius of the raindrop, and vt terminal velocity. Vt is equal to called as terminal velocity. What is remember terminal velocity? Attaining equal velocity, same velocity, constant velocity. Because you know when the rain is falling from top, highest position, after reaching to some point, because if this opposing force is not there, viscous force, what happens? The rain will fall with a huge velocity. It is having weight, so it will be damaging our head. So in order to protect our head, what happens? This viscous force will stop the velocity and will attain a uniform velocity. That uniform velocity is called as terminal. Now we are going to derive an equation for V terminal by using Stokes' law. Then kosam, I will take the raindrop. Let this is the raindrop. Let the radius be r. Let the raindrop is coming down. W is the raindrop weight. Okay. Okay, when the raindrop is coming down, the opposing forces acting on the raindrop, viscous force and also buoyant force, Fb. So these are things when the rain is coming down, weight, okay, and also I will give some more terms. Let the density of the raindrop be rho d, density of the raindrop. లేదా ఇంకైనా టర్మ్స్ తీసుకుందామా? ρ1 ρ2 అని బెటర్. ρ1 ρ2 అని తీసుకుందాం. ఓకే, ఐ విల్ రైట్ హియర్ ρ1 is the density of the raindrop. ρ1 is equal to density of the raindrop. Okay, and fluid air ρ2 is equal to density of the fluid air. Air యొక్క density ρ2 అనుకుందాం, raindrop density ρ1 అనుకుందాం. Okay, now we'll derive the equation. Now see here, raindrop is coming down, only one force acting here, and opposing force, viscous force and buoyant force. What is buoyant force actually? That means buoyant force and it is an upward thrust acting on the body when the body is fully or partially immersed in any fluid or liquid. In any fluid or liquid, if any body is partially or fully involved or immersed, then the upward force acting is called as a buoyant force, and the principle is called a buoyancy. Next thing I will be dealing that also after this derivation, buoyancy and other things. Now here you can see upward forces, buoyant force plus viscous force, upward force. Downward force, W is equal to mg, downward force. Now because the body, raindrop is coming down, so this force is more. So W is greater than Fb plus Fv. Now let us try what is this weight and Fb. Both are forces, downward, upward. Let us calculate weight. Okay, so weight and weight of the raindrop, that is mass into acceleration. What is the density of the raindrop? You go ρ1. So density is equal to mass by volume. Okay, so ρ1 is equal to m by volume. What is the volume? Raindrop is in the form of sphere. So 4/3 pi r cube. 4/3 pi r cube లేదా rho 1 into 4/3 pi r cube is equal to m. Now what is the weight? Rho 1 into 4/3 pi r cube into g. This is the weight. Okay, so the weight of the raindrop, and I'll put it here, rho 1 4/3 pi r cube into g. In the same fashion, upward is also acting another buoyant force, that is also equal to same. So అది కూడా సేమ్. ఎంత అవుతుంది ఇక్కడ రాస్తున్నాను చూడండి. I'll write it here. Density is equal to mass per volume, same volume again, 4/3 pi r cube లేదా rho 2 into 4/3 pi r cube into g, that is but upward force, thrust, buoyant force. This is downward force. Okay, now what did I given? Viscous force, that is Stokes law. I'll put it all the values here. Greater than, what is the buoyant force? Rho 2 4/3 pi r cube g plus Stokes law, that is viscous force, 6 pi eta r v terminal. So when the raindrop is coming downwards after some time, what happens? It attains terminal velocity and a uniform velocity, and acceleration enta, acceleration is 0, then v becomes v terminal, uniform. So therefore what happens? W minus fb plus fv is equal to actually ma, but because it is attaining terminal velocity, a is 0. So therefore what happens? W minus fb plus fv is equal to 0, or w is equal to fb plus fv. Now substitute all the values here. Rho 1 4/3 pi r cube g is equal to, what is fb here? Rho 2 4/3 pi r cube g plus 6 pi eta r v terminal. Take this to this side and take some common terms. 4/3 pi r cube common తీసుకుంటే I can write rho 1 minus rho 2. I am taking this side, and this is right side, 6 pi eta r v terminal. Pi r square here, 2 2s are 4, 2 3s are 6. Now I want v terminal, uniform velocity for the raindrop. So v terminal ఎంత అవుతుంది ఇక్కడ నుంచి? Take 3 to down. So ఇక్కడ ఆల్రెడీ ఎంత ఉంది మనకి? 2 by 3 కిందకు వస్తే 3 3s are 9. ఇంకా ఏ టర్మ్స్ ఉన్నాయి? Eta is there, so eta, okay, and r is cut here, nothing is there here. On the top ఇక్కడ ఏం మిగిలింది మనకి? పై క్యాన్సిల్ అయిపోయి ఇక్కడ r స్క్వేర్ ఉంది, తర్వాత g ఉంది ఇక్కడ, and లోపల బ్రాకెట్లో you are having rho 1 minus rho 2. This is equal to v terminal. Please check this formula once again. Okay, pi got cancelled, r square ఉంది ఇక్కడ, so 2r square g, 2r square g, 3 కిందకు వచ్చింది 9, eta కిందకు వచ్చింది v terminal. So this is the derivation. In intermediate examination, he may be asking for 4 marks or 6 plus 2. 6 marks plus 2 marks derivation. 2 marks some numerical. So what is the terminal velocity of the raindrop falling down? Is nothing but v terminal, uniform velocity, is equal to 2/9 r square g by eta rho 1 minus rho 2. Okay, is equal to terminal uniform velocity. Here rho 1 and rho 2 are the densities of the fluid, and the density of the raindrop and the density of the fluid air. And g 9.8 or 10 meter per second square. R is the radius of the raindrop, and eta, coefficient of viscosity, it will be given. Okay, remaining all are constants. Clear? Please note down. This derivation is very, very, very important. You can take it as 8 marks. Okay. Now after this, almost we are coming to end of the Stokes law and other thing. Now we are entering into the last part, that is buoyancy, Archimedes principle. Okay, apparent weight. Last point. See here. This derivation you have to practice at home in a rough book so that you will get it. Very, very easy derivation. Very easy derivation, very easy. You can solve it. Okay. Now let us go to the next part. So in the examination, sometimes he may ask some more applications also in Bernoulli's theorem. Actually, it is related, but anyhow I will tell that one. Exam lo marikonni kuda adagachchu vaadu entante what are the applications of Bernoulli's theorem? Inka unnai chaala. Bernoulli's theorem applications lo already I given Venturi meter. Some more are there. Entante in cricket, spin bowling. For example, this is a cricket ball. Okay. When the ball is not spinning, what happens? You can see the streamline. That means the fluid will be in this fashion around the cricket ball. Okay? Sorry, not like that. When the ball is not spinning, see here. Suppose when the ball is not spinning, this is the cricket ball. So you can see the streamlines of air will be in this fashion. These are the streamlines of air. Uniform on the top and down, it will be uniform. No variation, you can see. What are these lines? Streamlines of air. On the top and bottom, equal will be there. That is no difference in velocities. Ikkada velocity V1 aithe, ikkada kuda V1. There is no difference. This is what when the ball is not spinning. When the ball is not spinning. This is another application of Bernoulli's theorem. But when the ball is spinning, what happens? You can see now the streamlines will be in different fashion. In this way. In circular way. That means when the ball is spinning, you can see it is having some velocity. Apart from the velocity, it will have some drag also, air drag. This is called air drag. So on the top it will be more velocity V plus Vd, and in the down portion it becomes V minus Vd. Here V is the velocity with which the ball is throwing by the cricketer. When the ball is spinning, what happens? In the air, the velocity of the ball will be there, along with the drag also will be there, extra velocity. So on the top portion V plus Vd, and down it will be V minus Vd. So you can see there is velocity difference. On the top it is more velocity, pressure becomes less. So immediately the ball is lofted up. So ball is lifted up. ఎప్పుడైతే మీకు velocity difference, ఇక్కడ velocity difference లేదు because the ball is not spinning, just normal it is going. So when it is spinning, you can see apart from the velocity, air drag is there, another velocity. So total velocity how much acting on the ball? V plus Vd. Vd is air drag. And when it is coming down, what in opposite direction it is? You can see coming down V minus Vd. When air is dragging, you can see V plus Vd coming down. Okay? So this is an opposite direction, V minus Vd. So there is difference in the velocities now. So because of more velocity, less pressure, according to Bernoulli's theorem, ball is lifted up. Another example. Ide kaakunda you can take one more aerofoil. Aerofoil, that is aeroplane wing. Aerofoil. This is also called aeroplane wing. In the design of aeroplane wing also you can see these are the streamlines. These are the streamlines. These are streamlines, air lines, fluid air. Idantha fluid air and ingem kadu, all are fluid air. Okay? This is fluid, you can see. So that is why the aeroplane wing also it is designed in such a fashion that down it is flat, on the top it is in curvature. So because to crowd more streamlines of air. So here more velocity, okay, more crowded, so more velocity, less velocity down. ఇక్కడ ఎక్కువ ఉంటుంది velocity, pressure తగ్గిపోతుంది, వెంటనే there will be lift force. Okay, and this is the angle of attack of the wing, angle of attack. This angle of attack to the wing should be as minimum as possible. If more angle is there, attack of the air, the aeroplane cannot lift up. ఈ యాంగిల్ ఆఫ్ అటాక్ అంటే ఎయిర్ ఈ వింగ్ తాకినప్పుడు కొంచెం చిన్న యాంగిల్ ఉండాలి, యాంగిల్ షుడ్ బి వెరీ లెస్, ఇట్ షుడ్ బి మోర్ యాంగిల్, అరౌండ్ ఐ థింక్ 15 degrees ఆర్ లెస్ దెన్ 30 degrees, 15 degrees అనుకుంటాను, 15 to less than 30 degrees, 15 to less than 30 degrees, the angle of attack, very less it should be there. So otherwise what happens, the aeroplane cannot lift up. Okay, లిఫ్టింగ్ ఎలా జరుగుతుంది? ప్లెయిన్ పైకి వెళ్ళడం కానీ కింద రావడం బికాస్ ఆఫ్ బెర్నౌల్లిస్ థియరం. మోర్ వెలాసిటీ లెస్ ప్రెజర్. వెలాసిటీ పెరిగినప్పుడు ప్రెజర్ తగ్గిపోతుంది. సో ఇక్కడ చూడండి, పైన వింగ్ దగ్గర కర్వేచర్ ఇక్కడ మోర్ క్రౌడెడ్ స్ట్రీమ్ లైన్స్. మోర్ క్రౌడెడ్ మీన్స్ మోర్ వెలాసిటీ ఆన్ ద టాప్, లెస్ వెలాసిటీ in the down. Okay, more velocity, less pressure, body is lifted up. So like this, the aeroplanes will go up and come down by using Bernoulli's theorem. Please note down, this is the extra part I am telling you. Actually it is not there in syllabus, but still for understanding better manner of the application of Bernoulli's theorem. Clear? Now let us go to the last one. Let us go to the last one, please. Last part, that is buoyancy, Archimedes principle. Okay. Very important last part. Just now I was telling about what is buoyant force, buoyancy, Archimedes principle. Okay. Let us try to understand the term buoyancy. See here, what is Archimedes principle, Andy? What is Archimedes principle? See here, Archimedes principle. We all know, see here, suppose this is a vessel full of water. Now, when any body, you can see some bodies will sink into the water, some will float inside, and some will float on the surface of the water. Now, why those things? Some are sinking into the water, some are floating inside, some are floating on the surface. Now, what is Archimedes principle? When any body is immersed fully or partially inside a liquid, an upward thrust is acted. That means the body will be displacing some fluid. So it is also losing some apparent loss of weight. The body ఎప్పుడైనా నీటిలో వెళ్ళినప్పుడు we will be losing some apparent loss of weight. That loss of weight is equal to the weight, the displaced liquid weight. The apparent loss of weight is equal to the weight of the displaced liquid. Body immerse చేసినప్పుడు ఏం జరుగుతుంది? Upward thrust act అవుతుంది బాడీ మీద. Thrust will be there, upward thrust. And that is called as buoyant force. And the principle is called as buoyancy. When a body is partially or fully immersed in a liquid, upward force is acting on the body, thrust. Okay? So it is losing some weight apparently. That apparent loss of weight is equal to the weight of the displaced liquid. That is Archimedes principle. Now we will try to explain here. Suppose the weight of the body is greater than upward thrust. Upward thrust. Weight is greater than upward. Then what happens to the body? Body will sink like this. Body will sink. Here what happens? Weight of the body is greater than upward thrust. First case. Suppose second case, now weight of the body is equal to thrust. Then it will float inside. Okay? Weight of the body is equal to upward thrust. Float inside. Float inside the water or fluid. ఇక్కడ సింక్ మునిగిపోతుంది. థర్డ్ వన్, if weight of the body is less than upward thrust. Upward thrust కన్నా weight less ఉంటే ఏముంది? Floats on the surface. Floats on the surface. These are also called as loss of flotation. These are also called as loss of flotation. అదవుతుందా మీకు? If weight is more, body will sink. Then upward thrust. If weight is equal, it floats inside the water. If it is weight is less than thrust, thrust force ఎక్కువైంది అనుకోండి, weight తక్కువ, body will float on the surface. Like wood, dry wood. Like a plastic cover filled with water inside the water. Like an iron stone goes inside the water. Iron stone is sinking, weight is more. Plastic bag filled with water floating inside, weight is equal to thrust. Dry wood floating on the surface, weight is less than the thrust. Now how to calculate the weight? See, already we know weight is equal to m into g, or density is equal to mass per volume, or rho into v is equal to m, or rho vg is equal to weight. Weight means downward, weight of the body. So this is the weight, density of the body, volume of the body into acceleration due to gravity. Now when the body is immersed in the liquid, see when the body is immersed in the liquid, ఏం జరిగింది ఇక్కడ? Sometimes completely it may be inside, sometimes it may be partially, you can see. Sometimes completely it may be immersed, అంటే మొత్తం వాల్యూమ్ అంతా ఇమ్మర్జ్ అయిపోయింది. అంటే ఇక్కడ వాల్యూమ్ ఆఫ్ ద బాడీ ఈజ్ ఈక్వల్ టు వాల్యూమ్ ఆఫ్ ద ఫ్లూయిడ్. Sometimes total body will be immersed inside the liquid. అప్పుడు వాల్యూమ్ ఆఫ్ ద బాడీ ఈజ్ ఈక్వల్ టు డిస్ప్లేస్మెంట్ అంతా వాల్యూమ్ ఆఫ్ ద ఫ్లూయిడ్. బట్ ఇక్కడ ఏమైంది, ఇది టోటల్ వాల్యూమ్ ఇక్కడి నుంచి ఇక్కడ వరకు, ఓన్లీ సమ్ పార్ట్ ఈస్ ఇన్వాల్వ్, సమ్ పార్ట్. సో దిస్ ఈజ్ ద వాల్యూమ్ ఆఫ్ ద ఫ్లూయిడ్ హియర్. సో ఇక్కడ చూడండి పూర్తిగా ఇన్వాల్వ్ అవ్వలేదు. యూ కెన్ సీ ద టోటల్ బాడీ ఈజ్ నాట్ ఇన్సైడ్ ద లిక్విడ్ ఫ్లూయిడ్, ఓన్లీ సమ్ పార్ట్ ఈస్ immersed inside the liquid. So that is called as the volume of the body, which is equal to the volume of the fluid. So what will be the upward thrust now? Upward thrust, that is U, is equal to volume of the fluid, density of the fluid, volume of the fluid into gravity. So what is the upward thrust acting on the body? Volume of the fluid. How much part it is displaced? Water. Okay? Volume of the fluid. Density of the fluid. Water, if density you know, 1 gram per cc, centimeter cube, cgs, or 1000 kg per meter cube in mks. mks value anta density of water 1000 kg per meter cube. Ade cgs lo aithe 1 gram per centimeter cube. So when these two are equal, when you can see, when these two are equal, what happens? The body is floating. So the thrust is equal to it. That means density of the body, volume of the body, gravity is equal to the density of the fluid, volume of the fluid into gravity. G gets cancelled. So what is the important formula here? Density of the body, volume of the body is equal to density of the fluid, volume of the fluid. This formula is very very important in solving numericals. Entadi rho density of the body into rho b, VB, volume of the body is equal to a condition idi, second condition, floating inside the water. Okay, complete ga మునిగిపోవచ్చు లేదా కొంచెం పార్షియల్ కూడా ఉండొచ్చు పైన. Then also you can apply this formula. Okay, rho b VB is equal to rho f VF. This is density of the body, volume of the body, density of the fluid, volume of the fluid. ఇప్పుడు చెప్పాను కదా మొత్తం మునిగిపోతే that is equal to the volume of the body is equal to volume of the fluid. సగం మునిగింది అనుకోండి, కొంత పార్ట్ ఫ్రాక్షన్. సో దిస్ పార్ట్ ఈస్ కాల్డ్ యాజ్ ద వాల్యూమ్ ఆఫ్ ద ఫ్లూయిడ్ డిస్ప్లేస్డ్. అంటే దిస్ వాల్యూమ్ ఆఫ్ ద బాడీ ఈస్ నథింగ్ బట్ వాల్యూమ్ ఆఫ్ ద ఫ్లూయిడ్, దట్ పార్ట్. క్లియర్? ప్లీజ్ నోట్ డౌన్, దీస్ ఆర్ వెరీ వెరీ ఇంపార్టెంట్ ఇన్ సాల్వింగ్ న్యూమరికల్స్. లెట్ us go to the next one, density and relative density. Density and relative density. We all know what is the density of the body, mass per volume. మనందరికీ తెలుసు డెన్సిటీ అంటే ఏంటి, మాస్ పర్ వాల్యూమ్. ఓకే, వి ఆల్ నో వాట్ ఈస్ డెన్సిటీ. డెన్సిటీ అంటే ఏంటి, సాంద్రత, మాస్ పర్ వాల్యూమ్. బట్ వాట్ ఈస్ రిలేటివ్ డెన్సిటీ? దిస్ ఇస్ ఆల్సో కాల్డ్ ఎ స్పెసిఫిక్ గ్రావిటీ. సో రిలేటివ్ డెన్సిటీ అంటే ఏంటి, వెయిట్ ఆఫ్ ద బాడీ ఇన్ ఎయిర్ బై weight of the body in air minus weight of the body in air. That is loss of weight in water. This is also called as loss of weight in water. Very very important formula. What is relative density? Weight of the body in air by weight of the body in air minus weight of the body in water. This is loss of weight inside water. ఈ రెండింటి యొక్క రేషియో రెండు కూడా వెయిట్లే కాబట్టి రిలేటివ్ డెన్సిటీ డస్ నాట్ హ్యావ్ ఎనీ యూనిట్స్ అండ్ డైమెన్షన్స్. అదేవిధంగా ఒక బాడీ ఏదైనా ఇచ్చారనుకోండి, రిలేటివ్ డెన్సిటీ ఎలా కడతాం? ఎనీ బాడీ, డెన్సిటీ ఆఫ్ ద బాడీ ఇన్ ఎయిర్ బై డెన్సిటీ ఆఫ్ ద బాడీ ఇన్ లిక్విడ్. దిస్ ఈజ్ ఆల్సో కెన్ క్యాల్కులేట్ రిలేటివ్ డెన్సిటీ. Density of the body in air to that of density of the body in water. Okay, like that also you can calculate the relative density. Or weight of the body in air by weight in air minus weight in water, loss of weight. This is also equal to relative density or specific gravity. These are very very important in solving numericals in NEET and also MCET examinations. Now the last part of the chapter, that is part 2, fluid mechanics or mechanical properties of fluids, is surface tension. The last topic in this one to end of this chapter, that is surface tension. What is surface tension? What is surface tension? ST. See, this is a natural phenomenon you can observe. Suppose this is the water. Okay. Now you can observe in some places on the surface of the water, some small insects will be floating on the surface of the water. How? But human beings cannot walk on water because of heavy weight. That means the upper part will behave like a thin elastic membrane. Thin elastic membrane. Upper part of the water will behave like what? Thin elastic membrane. Thin elastic membrane పనిచేస్తుంది అన్నమాట. అందువల్ల చిన్న చిన్న క్రిమి కీటకాలు, ఇన్సెక్ట్స్ విల్ బి ఫ్లోటింగ్ ఆన్ ద వాటర్. తర్వాత చూడండి, మీకు ఈ అప్పుడప్పుడు మనకి కార్పొరేషన్ నుంచి ది శానిటరీ ఇన్స్పెక్టర్ విల్ కమ్ అండ్ డ్యూ టు eradicate these mosquitoes, they will be pouring some liquid and water like DDT and another. That is what? Contaminating the water. So when you pour the DDT or whatever thing on the water, it will reduce surface tension. Or by heating water, it reduces surface tension. So what is surface tension? It is the force acting per unit length. It is the force acting per unit length. When it reduces the surface tension, the insects will go down and they are killed. So like that, the mosquitoes are killed by using those materials by the sanitary inspectors. That means because of that they will be floating, but by contaminating you can reduce the surface tension. So it is the force acting per unit length. Units ఏంటి? Newton per meter in SI system or dyne per centimeters in CGS system. So it is a natural phenomenon. Surface tension is a natural phenomenon. Clear? And because of this only, raindrops are spherical in shape. Raindrops are spherical in shape. In the examination they will be asking how raindrops are spherical in shape. Because these will try to occupy minimum surface area. That is why minimum surface area దేనికి వస్తుంది? Sphere కి. అందువల్ల raindrops are spherical in shape. Okay? So due to the surface tension phenomenon only, what happened? Raindrops are spherical. ఇందువల్ల it will try to occupy minimum surface area. Because out of all the bodies, sphere surface area is very less. So that is, it is spherical in shape. One important question, 2 marks in IP. Why raindrops are spherical? Due to surface tension, it will occupy minimum surface area. That is why it is spherical in shape. Okay? So this is very important. And you can write the dimension formula also. ml t power minus 2 by L. So m t power minus 2. That is the dimension formula for surface tension. In the same way, surface energy is also there. The formula is work by area. The minimum amount of work required to remove the sphere to the top portion of the layer. From the bottom to the top. Work done in removing the sphere. So, దీనికి formula కూడా ఉందండి surface energy కి work by area. Work కి మళ్ళీ dimension formula ఏంటి? ml square t power minus 2 area కి L square. L square gets cancelled. M t power minus 2. అంటే surface energy కి surface tension both have same dimension formulas. M t power minus 2, M t power minus 2. Clear? So these are very very important in examination point of view. Surface tension and surface energy. Now let us go to the next one. Okay. Angle of contact. Angle of contact. These also they are asking in the examination. What is the angle of contact? Angle of contact theta. See, we all know, for example, this is a bowl, this is a glass tube, this is water, please, normal water. And I'll take another one, mercury, high viscous, again glass tube. So if you see the mercury, it will be little hogging and little depressed down. This is mercury. Here the surface of water is sagging and here it is hogging. And we all know capillarity. Capillarity. So what is the capillarity principle? Due to the capillarity means the rise or fall of the liquid inside the glass tube due to surface tension of the liquid or fluid is called as capillarity. So when you put the glass tubes inside the water ones, and in mercury you can see water is raised to some height, but in mercury it is dropped down. You can see mercury kenda padipindi, depression. So ikkada enti, if you draw a tangent touching the surface, here I am drawing a tangent here, this is a tangent, and here also I will draw a tangent. A, B, this is C. Here this is the angle of contact here, and for here A, B, C, this is the angle of contact. You can see for water the angle of contact is acute angle, and for mercury the angle of contact is obtuse angle, and almost it is taken as 135 to 140 degrees. For mercury the angle of contact is taken as 135 to 140 degrees. But for water it is acute angle, and for all practical purposes it is taken as 0 degrees. Okay? Therefore, in surface tension expression, that is HR dz by 2 cos theta derivation expression. Okay? Surface tension expression, H height of the liquid level, R radius of the glass tube, rho density of the fluid, G acceleration due to gravity 9.8 or 10 meter per second square, and cos theta is the angle of contact here. Water మరి చూసినట్టయితే అది చాలా చిన్నది యాంగిల్, acute angle ఇది. Almost it is less than 90, you can see the angle. ABC angle, you can see. ABC angle is 90, less than 90. And here you can see ABC, it is obtuse angle, more than 90 for mercury. So nearly it is taken as 135 to 140 for mercury, angle of contact, and for water it is almost taken as 0 degrees. So when you put here, surface tension formula becomes HR rho Z by 2. Okay? And surface tension always acts along the perimeter. Please make a note. Surface tension always acts along the perimeter. Okay, this is the ball. Okay, na? Suppose this is a water level rise here. You can see. So this is the angle of contact. This is surface tension. Always acts along the, this is the component, T cos theta, and this is T sin theta. So this component is unaffected. Only T cos theta is acting along the perimeter, 2 pi r. So always the surface tension acts along the perimeter of the body. Clear? And these are the formulas you have to remember in surface tension. And last one, that is excess pressure. Last one is excess pressure in a liquid drop and a soap bubble. Excess pressure in a liquid drop and a soap bubble. This is the last one to end of the chapter. Please make a note. In the examination they will be asking as a bit questions, excess pressure in liquid drop. Last one. Okay, right. So what is excess pressure inside a liquid drop and a soap bubble? See, if you observe carefully, normal liquid drop will have only one surface area. Normal liquid drop. Normal liquid drop. For soap bubble, if you take, it has 2 layers practically. For soap bubble, okay, for soap bubble you have 2 layers. Soap bubble చూసినట్టుగా it has 2 layers. So అంతేకాకుండా if you observe carefully, the excess pressure, always acts along the area, and surface tension acts along the perimeter. Pressure acts along the area, pi r square, and surface tension acts along the perimeter. So for this, from this you can see pi gets cancelled, R gets cancelled, P is given by 2T by R. So for ordinary bubble, excess pressure is given by 2 times surface tension value by R. R is the radius of the bubble. In the same way, if you take soap bubble, it has 2 layers. Therefore, అప్పుడు ఏమవుతుంది, ఇది 2 times కాబట్టి దీన్ని 2తో మల్టిప్లై చేయండి. I'll write it here better. P into pi R square is equal to T into 2 pi R into 2 times. For soap bubble, it has 2 areas, surface areas, 2 రెట్లు. సో అప్పుడు ఇది ఏమవుతుంది, దానికి 2 times వస్తుంది వాల్యూ. అంటే excess pressure, you can see again, R gets cancelled. Okay, pi gets cancelled. So excess pressure is given by 4T by R. T is surface tension, R is radius of the soap bubble. Soap bubble ki 2 areas గా తీసుకోవాలి. 2 areas, 2 సర్ఫేస్ సోప్ బబుల్ కొంచెం చూడండి, మీకు థిన్ ఫిల్మ్ ఫామ్ అవుతుంది పైన, అందువల్ల 2 సర్ఫేస్ ఏరియాస్ ఉంటాయి. సో ఇన్ సచ్ కేసెస్ you'll get 4T by R. T is surface tension, okay, and R is radius of the bubble, P is excess pressure. So these are the formulas we have to use in the examination for numericals. Very, very important. So I think this is the end of the fluid mechanics chapter or mechanical properties of fluids. Again, we'll be meeting in the next topic.